Hi, welcome everyone. This is Mr. Trocino again. This is our fourth week of distance learning. So for this week, we're going to cover sequences and then eventually end with the introduction of arithmetic and geometric sequences. So the topic today is slightly different from what we've been um, doing for the last 3 weeks, but you will notice some similarities it has. Eventually, I hope you do make connections on exponential progression and geometric sequences. So before we begin our lesson, let's go over the online guidelines for our safety. Okay, so again, please be reminded that the PGCPS administrative procedures regarding appropriate use of technology, social media, and email continue to apply to our online instruction. Of course, we are on this particular statement again. This particular statement is not pretty much applicable in our current setup as this session is a pre-recorded one. However, we will interpret this statement as the recording could not be shared without the instructor's consent. So that's mine. So if you would actually like to share it with a friend who you think would benefit from watching the video, do let me know so that I can actually give a verbal consent, or we could do it written if you could send me an email asking for permission. That way we protect each other. Anyways, a description of the applicable procedures is provided online in the Student Rights and Responsibilities Handbook. Thank you for your cooperation. As I've mentioned, the Student Rights and Responsibilities Handbook is located at the PGCPS portal, or if you don't want to bother with that, you could just, of course, go through the Google Classroom, and if you look way at the beginning of the stream, so that would be way at the bottom, you would actually find a link there that takes you straight to the Student's Handbook. Okay, so now that this is out of the way, let us actually begin our lesson. So the lesson for today is about sequences. Here we go. Okay. So introduction to sequences, recursive and explicit formulas. Actually, from the previous set of activities that I gave you, I did notice some of you actually providing me formulas for defining the pattern of a particular sequence using recursive formulas. I expect you guys to give me explicit formulas, but some of you do give me recursive formulas. So this week, we're actually going to differentiate between the two. Okay, but before we actually go to the lesson proper, let us look at the objectives. So at the end of these lessons, students are expected to define a sequence using recursive and or explicit formulas. So pretty much from the work I'm going to give you, I'm going to give you a sequence, and you are to figure out the sequence formula using a recursive and an explicit formula notation. Okay, number 2, you are to differentiate between recursive and explicit formulas from each other and use each other to help you determine what the other formula is. So if I give you a recursive formula, all right, later I would ask you to give me an explicit formula. If I give you an explicit formula, you could give me a recursive formula. Okay, then finally, right, so we're going to be defining and differentiating arithmetic and geometric progressions. So this, the last objective is not too much. We're just going to tackle the main definition. Once you see it, I'm very sure that it would be very familiar. Okay, and hopefully you will actually find some connections with some of our previous topics. Although, as I mentioned, because we were going over exponential functions lately, this would be a bit of a slight detour. But later, you will, of course, see some connections with exponential functions. Sequences. Okay. So pretty much a lot of you would have your own definition of sequences, and I'm pretty sure your definitions would be correct. Formal definition of a sequence is that it is a set of numbers that follow a particular rule. Okay, so the rule may be algebraically stated. Sometimes you could just pretty much just define it through words, although you have to be very specific of the words you use so that it is not confused with a particular rule. And where its domain is the set of natural numbers. Okay, so when you say the domain is the set of natural numbers, that means the numbers that you substitute for the variable has to begin with 1, then 2, then 3, then 4, and so on and so forth. Natural numbers are counting numbers. So you cannot substitute fractional numbers like 1/2 or 10.75. It has to be positive numbers. 1, 2, 3, 4, 5. Okay. So the rule is an algebraic notation, and this can be defined through either a recursive formula or an explicit formula. Okay, so this is what we're actually gunning for. So later, we'll be able to see how recursive formulas are different from explicit formulas. Okay, the next part, I've already defined it. Talking about the domain being the set of natural numbers. Okay, this one is very important, at least to understand the notation. So for sequences, we denote the nth term of a sequence as a sub n. This is like the y term. So in functions, usually we say it's that f of x is equal to something, or sometimes we just refer to it as y is equal to something. So for sequences, we replace that y or f of x with a sub n, okay, which is pretty much defined as the nth term. Okay, it is determined by its term number n. So the n here represents the x term. Okay, so later you will realize that this a sub n and n connection pretty much applies more to explicit formulas as opposed to recursive formulas. Although there are recursive formulas that does use n in its description of its rule, right? So the next slide, I think we'll go over the differences between explicit and recursive formulas. Aha, here we go. Here we go. A recursive formula is a sequence formula where the nth term is determined by algebraic manipulations of the previous terms. Okay, so to be able to create a recursive formula, you have to define a later formula by an algebraic expression in regard to its previous terms. For example, a sub n here is equal to a sub n minus 1 plus 2. All right, and then usually you will have to define the first term. So a sub 1 is the first term because notice it has the subscript of 1. So a sub 1 is the first term. That is term number 1. So term number 1 is -8. And notice here, the next term is determined by adding 2 to the term that comes before that. So later, we will actually see some examples on how this sequence can actually work, or how does it look like when expanded a bit. Another example of a recursive formula, a sub n is equal to 3 times a sub n minus 1. Again, we define the first term. So a sub 1 is equal to 1. So for recursive formulas, it is important to define the earlier terms, usually a sub 1 and a sub 2. Right? But if you will not define the rule based on more than one earlier term, then just defining a sub 1 should be sufficient. Sometimes recursive formulas define their nth terms by making use of two previous nth terms. But usually it's only one term. Particularly in this context, we're only going to define the next term by its previous term. An explicit formula is a sequence formula where the nth term is determined by algebraic manipulation of its term number n. All right, so for an explicit formula, you actually don't need to know what the previous term is. So it's like a direct substitution. So unlike a recursive formula, you need to go over each particular term to arrive at a particular nth term. For an explicit formula, you can simply jump to whatever term you'd like. A sub n is equal to negative 10 plus 2n. Right? So if you are looking for the fifth term, you simply replace the n by 5. So a sub 5 is equal to negative 10 plus 2 times 5, which is 10. So negative 10 plus 10 is 0. Right? Unlike recursive formulas, if you replace n by 5, so a sub n or a sub 5, the fifth term, is equal to a sub 5 minus 1. So that becomes 4. So a sub 5 is equal to a sub 4 plus 2. But the question is, do you know a sub 4? No, I don't. So you have to go back. Okay, so what is a sub 4? A sub 4 is equal to a sub 3 because it has to be one term before the fourth term, so that's the third term, plus 2. And then you ask the same question because you also don't know a sub 3. Eventually, you end up trying to figure out a sub 2 first, the second term, because the second term is just 2 higher than the first term. So once you've figured out what the second term is, you can now begin figuring out what the third term is, then fourth term, then fifth term, and so on and so forth. Now, although you might think recursive formula is a bit limited, recursive formula is actually very good in trying to determine simple patterns. Because once a simple pattern is observed, it is easy enough to generalize what type of sequence the rule follows. Okay? A second example of an explicit formula, we have a sub n is equal to 1/3 times 3 to the n. Now, this one looks like an exponential function. Okay? So if we're looking for the fifth term, a sub 5, that would simply be 1/3 times 3 to the fifth. 3 to the fifth is 243, and 1/3 of that is 81. All right? Unlike this one, you'll have to figure out each consecutive term before you actually get to the fifth term. All right, so let's see some examples on how these work for us. Okay, so here we have number 1. It's a recursive formula because notice you're given the nth term in terms of the previous term. Okay, and then you're also given the first term. So it says here a sub n, the nth term, is 5 times the previous term. All right, so that this is what number 1 means. Number 2, a sub n is equal to 6n plus 1. So this one is definitely determined by n. So number 2 is an explicit formula. Okay, So now that we have identified which example is a recursive formula and which sequence follows an explicit formula, you are to determine the first 5 terms of each sequence. Okay, so if you'd like to work on this on your own, you may pause the video, try to write down the first 5 numbers of each sequence, and then we can check your answers later on the next slide. Okay, I think that should be enough time for you to have paused the video and tried it on your own, and then unpause it to check your answers and see our solution. All right, here we go. So the way we solved it, we tabulated it so that we can actually see how it progresses. So number 1, as I mentioned, is a recursive formula, as a sub n is determined by multiplying 5 to the term previous to a sub n, which is a sub n minus 1. Okay, so to be able to see what the first 5 terms are, so here is the term number. So it's term number 1, term number 2, 3, 4, and 5. Okay, so a sub n is the term. So a sub 1, this refers to the first term. So the first term is already defined. It is 2. So we actually just have to write it down. A sub 1 is equal to 2. So once we write the sequence, it's more like 2, then the second term, right, which is defined as a sub 2, is equal to 5 times the previous term. So the second term is 5 times a sub 1. And a sub 1, as defined here, is actually 2. So a sub 2 is equal to 5 times 2. Thus, a sub 2 is simply 10. Okay? So the first term is 2, followed by 10. And if you follow the sequence, because you know that the next term is defined by multiplying 5 to the previous term, so 10 times 5, you actually get 50. So the third term is 50. Times 5 to 50, you get 250. That's the fourth term. And then times 5, you get 1,250. Okay, so notice how the recursive formula is used to obtain the terms of a sequence. So you need to figure out the previous term first before you actually figure out the next term. Now let's see how it works for explicit formulas. For explicit formulas, it's pretty simple because all you have to do is to substitute the term number for n. So if you're looking for the first term, remember, explicit formulas do not define the first term. It is only a recursive formula that would define earlier terms. A sub 1 is definitely defined there. So again, we have the term numbers 1, 2, 3, 4, and 5 because we are looking for the first 5 terms. A sub 1 is equal to 6. Then you replace the n by the term number, which is 1. So it's 6 times 1 plus 1. So eventually we have 7. The second term, a sub 2, is defined or is obtained by replacing n by 2. So 6 times 2, that's 12. Plus 1, we have 13. And if you continue doing this, you would actually get 19, 25, and 31. So those would be the first 5 terms of that particular sequence. Okay, so hopefully the 2 examples were enough to help you identify how to figure out the terms of a particular sequence given a recursive formula or an explicit formula. All right. Aha. Okay, so now we're actually going to look at some generalities and eventually proceed to the part wherein we are going to figure out a particular formula given the other rule. So recursive formulas require the knowledge of the relation of the previous terms and their progression to identify the next term. Thus, the first term a sub 1 should always be known. All right, so this is definitely what I've been emphasizing. So for recursive formulas, you need to know the previous terms, and you should definitely know what the first term is. So in terms of sequences, because our domain is the set of natural numbers, thus usually we don't use the zero term, a sub 0. We begin with an a sub 1. Explicit formulas are straightforward in the sense that determining the nth term, a sub n, only requires the rule and the value of n. Ha! This is also what I mentioned earlier. If you need to look for a sub 5, just substitute 5 for the value of n, apply the rule, and you automatically figure out your fifth term. Okay? All right. So hopefully that does give you, that does enlighten you on how you actually approach recursive and explicit formulas. The next slide will actually go over some examples. All right, and then we're going to identify their explicit and recursive formulas. Remember, recursive, you need to identify the rule to determine the next term. Explicit, you need to identify the rule to figure out a specific nth term. Haha! All right, so here we have 4 different sequences. Okay, so the question is to determine the recursive and explicit formulas for each sequence provided. So the first one begins with -10, then -7, -4, -1, and 2. The next one is 12, 7, 2, -3, -8. Third, we have 1,000, 100, 10, 1, and 0.1. And then for number 4, we have 0, 3, 8, 15, and 24. Haha. All right. Okay. So if you would like to actually try to figure out what the recursive and explicit formulas are for each of these 4 sequences, you may, of course, pause the video, right? Identify, solve for the recursive and explicit formulas for each, and then unpause the video to check your answer and see our solution. All right, I think that should be enough time for you to have paused the video, solve it, and then unpause the video to check whether you actually got your answers correct. Right, let's see now the answers. Okay, so we'll start off with number 1, of course. Okay, so if you look at number 1, so we have -10, -7, -4, -1, and 2. All right, I think we'll actually try and figure this out. I think it's easier for me to actually go over the solution by actually trying to talk about this while we're answering. So we'll switch to my whiteboard. Oops. It didn't switch to my whiteboard immediately. I think this one should get it. All right. Here we go now. All right. So in the previous example, we had -10. Apologize, I forgot the numbers. Let me just look at it, look at those numbers again. Aha! -10, -7, -4, -1, and 2. All right, so here we go. I have written them down now. All right, so the first thing we're going to see is to identify the recursive formula, because the recursive formula identifies the simple pattern. You just need to figure out how to figure out the next term using the previous term. So we focus on -10. So from -10, how do we get -7? So there would be several answers, right? Maybe we can square it first, then subtract a particular number. Maybe we multiply something. But let's start with something easy and see whether that formula sticks. Let's start with just adding 3. Right? So -10 plus 3 is definitely -7. From -7 going to -4, again, we add a 3. Right, so okay, that's good. We have the same pattern here. From -4 going to -1, we also add a 3. All right, okay, there's only one term left. Let's see if by adding 3 to -1, we do get 2. So from -1 to get 2, we add another 3. All right, so thus, the pattern in determining the sequence or in determining the next term is simply to add 3 to the previous term. Thus, we can now identify our recursive formula. So our recursive formula is a sub n, all right? Okay, the nth term, that is equal to whatever the previous term is. That's why we use the n minus 1 as a subscript, because it is one term earlier than the nth term. And then, whatever the previous term is, we simply add a 3 to that. Right? And then don't forget, as a recursive formula, you always have to define what your first term is, which is obviously the easiest one. The first term is simply -10. All right? I hope you got those. All right? I hope you got the recursive formula and also the first term. Remember, writing only the recursive formula is not altogether the most correct answer, as okay, so I do know that the next term is 3 higher than the previous term, but at what term do I begin with so that I actually have the same sequence as the one I'm seeing right now? So you always have to define the first term for a recursive formula. All right, now we go to explicit formulas. All right, so how do we determine an explicit formula here? Okay, so to determine an explicit formula, we simply look at the pattern. We keep adding 3. So this constant addition of 3 gives us a notion that this might be a linear function. All right? Okay, so if it's a linear function, then it should follow the form y is equal to mx plus b. All right? Now the m, the slope, is pretty much how much the next term or the next y value goes up or lower as you move one step towards the right. So from this term, as you go one term higher, notice that it actually went 3. And if you continue moving one term higher, each next term is 3 units higher than the previous term. Thus, this 3 is actually our slope. So we actually have one term here already. We already have 3x here. Okay, so we have y is equal to 3x. Now we have to figure out b. Now b, as we've been discussing earlier, b is the y-intercept. Now, as I mentioned earlier, sometimes I refer to the y-intercept as the zeroth term. The reason I keep mentioning zeroth term for that is, of course, to make a connection with this particular topic. Now, because it is the zeroth term, that means it should be the term that comes before the previous term. Okay. So let's recap. So we do know that the sequence progresses as -10, -7, -4, -1, and then 2. This is the first term, the second term, the third term, fourth, and fifth. So if we are looking for the zeroth term, the zeroth term should be the term before the -10. Okay, so if this follows the same rule, how are we actually going to figure out the zeroth term? So notice as you go higher, as you go to the next term, you actually add 3. So if you move back, that means the previous term should actually be 3 units smaller than the next term. So -10 minus 3, that means the zeroth term is simply -13. So thus, we have our linear formula y is equal to 3x plus -13, because -13 is our y-intercept. It is our zeroth term. However, as I mentioned earlier, for an explicit formula, we do not use y and x. We actually use a sub n and n. So for an explicit formula, we replace the y with an a sub n, and we replace the x with just an n. Now this one, the plus -13, we'll simply write it down as -13. Okay, thus we now have the recursive formula, and we have the explicit formula. All right, so I hope that this explanation is quite clear. Remember, if you actually have any questions, definitely go over to our weekly Google Docs, type in your questions there. So during the time that I am active over there, I see your questions, I definitely answer them. That way, you actually learn what you specifically don't understand. Now, the reason why I post it in Google Docs is that maybe some people are not as courageous in asking questions. So by you asking a particular question, they actually gain insight from from how I answer. All right. Okay. So now let's see what the answers are also for the next examples. Aha. All right. Oh, I'm sorry. I'm going to replace these people. A sub 1 should be -13. All right. So when I upload this, the text would, of course, be correct. Oh, I'm sorry. A sub 1 should be -10. What am I talking about? However, I did get the explicit formula correctly. Good job, Mr. Tricino. right? So the next slide, actually, I think I only give out the answers. Okay, so hopefully you should be able to work it out on your own, or if you'd like, you can ask me in the Google Docs and I can provide the solution for each of those example sequences on how we were able to define the recursive formula and the explicit formula. All right, so number 2 is a linear progression. So it should be very similar to number 1. It should have an a sub n is equal to a sub n minus 1 and either a plus or minus. And then, of course, we define the first term. Its explicit formula should also be somewhat linear in nature. Okay, so very similar to number 1. Number 3 is an exponential progression. Right? That means the next term is determined by multiplying a particular term to the previous one. So here, a sub n is obtained by multiplying 1/10 or 0.1 if you prefer it in decimal, 0.1 or 1/10 times the previous term. And the first term is definitely a sub 1. Explicit formula, a sub n is equal to 10,000 times 1/10 raised to the n. Remember, for the explicit formula, for the most part, okay, for the explicit formula here, this one is based from the form y is equal to mx plus b, and b is the y-intercept. So it requires the 0th term for the b part. So this one should be the 0th term. Next week, when we start focusing on arithmetic and geometric progression, we will not bother so much with the 0th term. Explicit formula for an exponential progression, because it's very related to the exponential functions, this should be of the form y is equal to a times m raised to the x. So thus, a is also a y-intercept, thus it should also be a 0th term. So even though the first term is 1,000 in the sequence, you actually need the term before that in your explicit formula. Number 4 is the most challenging. It's a quadratic progression. Okay, so if you've known me, you do know that I do love putting in something new, right? Thus, just so that you are exposed. So notice how difficult or how different a quadratic progression is. Its recursive formula is a sub n is equal to a sub n minus 1 plus 2n minus 1. Okay, so notice it makes use of the previous term and it also uses the term number. Okay, so that's definitely different from the linear progression. It seems like its explicit, its recursive formula is a combination of a recursive formula and an explicit formula. However, this one is still classified as a recursive formula because it alludes to the previous term, to a sub n minus 1. Its explicit formula is actually surprisingly much shorter. A sub n is equal to n squared minus 1. Right? So if you've noticed the progression of number 4, 0, 3, 8, 15, 24, you should be able to see that this is quadratic in nature. For more on this, you can definitely refer to the Google Docs and you would see an example I solved which follows a quadratic progression. All right, so this is pretty much the last topic we're going to be covering, arithmetic and geometric sequences. So an arithmetic sequence is a sequence where the next term is obtained by adding a constant to the previous term. This may be thought of as a linear progression. Aha! So a linear function is like an arithmetic sequence. So in our previous examples, the first two follow an arithmetic sequence. Okay, now remember, even though I mentioned here, it's adding a constant, take note the constant can either be a positive number or a negative number. So even though I'm only using the word adding, it also implies I could be subtracting, because if I add a negative number, the effect is more like subtracting a number. Okay, so just to make sure that it all falls under the same group, I am just referring to it as addition of a constant. So this is how you identify whether a sequence is arithmetic in nature. A geometric sequence, on the other hand, is a sequence where the next term is obtained by multiplying a constant. Okay, so for arithmetic sequences, you only need to add a constant. Now remember, the constant can be a positive or a negative number. Okay, for a geometric sequence, we multiply a constant. Now, take note, as I've noticed in previous works, sometimes you think of exponential functions as like division. That is true. However, take note that the controlling operation that we need is multiplication. Thus, if you realize a particular number or a particular term is obtained by dividing the previous term by 3, right? So the pattern is the next term is obtained by dividing by 3. That division of 3 is equivalent to multiplication of the reciprocal of 3. So division by 3 is the same as multiplying by the reciprocal of 3, which is 1/3. So division of 3 is the same as multiplication by 1/3. And 1/3 is the constant that we actually need, right? I noticed that some of you actually understand the concept. However, you miss out on the part to convert that division operation into a multiplication operation. It is only a simple matter of taking the reciprocal of the divisor. So if you know you're dividing it by 3, thus you are multiplying it by 1/3, right? So the geometric sequence can be thought of as an exponential progression, right? So it's very similar to exponential functions. Now for this one, linear functions, this has been for a while, but definitely linear functions are very, very important in the study of algebra. So you should never forget how to solve linear functions. All right, I think the next slide will be examples of arithmetic and geometric sequences, and I think you're supposed to identify them. Let's see. Aha, right, so we only have 3 sequences here. So in the 3 sequences provided, you are to identify whether it is an arithmetic or geometric sequence. Now, you are also to justify your answer. Why do you think number 1 is an arithmetic sequence? Why do you think number 2 is also arithmetic? What about 3? Is it arithmetic or geometric? So you have to, of course, justify why your choice is arithmetic or geometric, right? So as usual, if you would like to try this out on your own, you may pause the video, try to answer this on your own, and then later unpause it so that we can actually see the solution and the answers. Okay, I think that is enough time to actually pause the video, try and figure out the answers by yourselves, and then unpause the video to check the answers. So here we go. This time for the big reveal. Aha! All right. So number 1 is an arithmetic sequence. Okay, so how do we know it's an arithmetic sequence? the next term is determined by adding 3 to the previous term. So we're adding a constant, and that constant is 3. So let's see. 6 plus 3, it does give us 9. Plus 3, it does give us 12. Plus 3, it gives us 15. Plus 3, it gives us 18. So therefore, this sequence, 6, 9, 12, 15, and 18 is definitely an arithmetic sequence. Right? Number 2, 3, 6, 12, 24, and 48. It is a geometric sequence. It's a geometric sequence because the next term is determined by multiplying 2 to the previous term. So you keep doubling it to get the next term. So 3 times 2, you get 6. That makes sense. 6 times 2, you get 12. That's good. 12 times 2, that's 24. 24 times 2 is definitely 48. So thus, this sequence here, 3, 6, 12, 24, and 48 is indeed a geometric sequence. All right. What about number 3? All right. Let's look at number 3. Let's see how many of you actually got it correct when you work on your own. So number 3 is actually both types. It's both an arithmetic sequence and a geometric sequence. It is arithmetic in nature because you keep adding 0 to the previous term, right? So 2 plus 0, that's 2. Plus 0, that's 2 again. Plus 0, that's 2 again. Plus 0, that's definitely 2 again. All right, so definitely it does satisfy the criteria for an arithmetic sequence. What about for geometric? Geometric because of constant multiplication of 1. That means to determine the next term, you simply have to multiply the previous term by 1. Let's see. 2 times 1 is 2. Times 1 is 2 again. Times 1 is 2 again. Times 1 is 2 again. All right. So thus, example number 3 is definitely both an arithmetic sequence and a geometric sequence. Right? So I hope you guys learned something good this week. And I hope you are able to do the activities I will be posting later. And remember, if you do have questions, do not hesitate to put them on our weekly Google Docs. I am always attaching that on the materials I sent over. So definitely put your questions over there. All right. So I hope you guys are staying safe, right? So we're now at the month of May, which is great. So it's only a few more weeks, or we can just say next month, school would be ending. So I'm not sure whether we would be seeing each other physically before then. All right. But definitely, let's just hope that everyone stays safe so that definitely next school year, we can actually see each other roaming the halls of Duval, except for the seniors, of course. If we see you in the halls of Duval next year, we will not be as happy as could be. Anyways, stay safe. This is Mr. Tricino. I hope, again, I hope you guys learned something. So this week, bye-bye.